If x and y are normed to linear spaces, we can define Bxy as the set of all bounded linear operators which map from x to y and whose domains are the full space X. And this set becomes a vector space if we define suitable operators for the addition of two operators and multiplication of an operator with a scalar. And we can do this in the pointwise manner shown here. Using these definitions, it's quite straightforward to check that both s plus t and alpha times t are again bounded linear operators, and that all the axioms of the vector space are satisfied. In particular, in the vector space, the zero element of the space is the operator which maps every element x to the zero element of the space y. This linear vector space structure is really useful for us in studying linear operators, and we'll use it very often on our course. As a side interest, it's also noteworthy that if we limit our attention to the operators which map from a single space x back to the space x, then the space Bx has even more algebraic structure, since we can also define a product of two operators s and t as the composition of these two linear mappings. And with this additional third operation, the space Bx becomes an algebra, and this leads to the study of so-called operator algebras, which is a very important branch of functional analysis. And returning to our case where t maps from a space x to y, we define the norm of a bounded linear operator to be the supremum of the values of the norm of tx over all vectors x which have norm at most 1. One way of visualizing this definition is to think of the operator, the norm of an operator t, as the smallest upper bound for how much the operator t can stretch the norm of a vector x. But the word stretching here is not quite accurate, since t, of course, doesn't always increase the norm of the vectors x, but instead it's completely possible that, for example, all the images of vectors of x of length at most 1 have norms less than 1/2, in which case the norm of the operator in question would be at most 1/2. And again, in terms of mappings, the norm of the operator is also the radius of the smallest ball in y centered at 0, which contain the image of the unit ball of the space x under the mapping T. And computing the norm of a concrete operator T can sometimes be quite challenging, but in general this still involves only 2 steps. First, we take an arbitrary element x from the space x, and we estimate the norm of tx upwards with a constant m0 and the norm of x. In addition, we try to do this in a way that the constant m0 here is as small as possible. And by definition, this kind of an estimate already means that the norm of t must be at most m0, since the norm is defined to be the least upper bound that these types of quantities have when x has norm 1. And in the second step, we try to find a particular vector x0 such that the norm of tx0 is exactly equal to our constant m0 and the norm of x0. And if we can do this, we have shown that the supremum in the definition of the norm cannot be any smaller than m0. And because of this and the first part, we conclude that the norm of t must be exactly equal to m0. But in general, it's not possible to find an element x0 such as the one in part 2.1 here, but instead, more generally, we can achieve the same conclusion if we can instead find a sequence of vectors xk for which the ratios between the norms of txk and xk converge to m0 as k goes to infinity. And this second option is required on infinite dimensional vector spaces because the supremum in the definition of the operator norm is in general not achieved as a maximum. This can even happen in the case of quite simple operators. The difficulty of the computing of the operator norm usually comes from the requirement that the constant m0 here should be the best possible constant and smallest possible. But it's also worth noting that the part 1 by itself already gives us an upper bound for the norm of the operator t, and because of this, the part 1 by itself can already be quite valuable and useful. And moreover, it can sometimes or even often be quite challenging to construct a suitable vector x0 or the sequence xk in part 2 of computing the operator norm. The operator norm we've defined has some quite nice properties. First of all, for any vector x, we can estimate the norm of tx with the product of the operator norm and the norm of x. This estimate is of the same form as the estimate in the definition of the boundedness of an operator, shown here, and by definition the operator norm is in fact the smallest possible constant m, which we can use in an estimate of this form for all vectors x. And in addition, if S is another bounded linear operator from Y to another normed linear space zeta, then the norm of the composition of these two operators S and T can be estimated from above by the product of the two operator norms. The operator norm is defined for all elements of the space Bxy, and in fact this vector space becomes a norm to vector space together with the operator norm. And when talking about normed spaces, one of the first questions, as we recall, is whether or not the space is complete. And as the last result in this video, we have the fundamentally important theorem shown here, which tells us that the space Bxy is a complete normed space whenever the space Y is a Banach space. The proof is presented in detail in the lecture notes, and it can also be found in all introductory level books on functional analysis. The proof of the completeness of Bxy begins, as typical, by letting Tk be an arbitrary Cauchy sequence in our normed space. Then, for any fixed element x, we can deduce that also the sequence of images Tkx is a Cauchy sequence, but now in the space Y. But since we assume that the space Y is a complete space, this Cauchy sequence of the images has a well-defined limit for every vector x. In the next step of the proof, we define a mapping T from the space x to y in such a way that for any x, the image Tx is defined to be precisely the limit yx in our previous step. So essentially, we are here guessing what the appropriate limit T, operator T, of our Cauchy sequence should be, and our guess is motivated by the fact that the limit T should definitely have the property that the images tkx of a fixed vector x converge to the image tx of the same vector x. And finally, in the last step, which requires perhaps the most effort, we verify that T is indeed a linear and bounded operator and therefore belongs to the space Bxy, and we also prove that the sequence Tk converges to T in the operator norm as k goes to infinity.